So I'm Sebastian Cespedes. So I'm going to talk about some work we're about to publish with Philippe and Anne. And this is about trying to look for signatures of modified gravity on the CMB, especially on B-modes. So I'm going to explain a little bit what are B-modes, because the main thing we're going to look at are gravitational waves, and what will be the signal from them. So we're going to take what will be the signatures on the B-mode from a modified speed of sound for the tensor modes, then what will be the signature for a graviton mass, and then after that we're going to see what will happen if we have bigravity and if we include the instability. So what will happen with all these cases. So we have that from inflation there is a production of gravitational waves because the graviton has some polarization modes that are produced during inflation. They leave the horizon. They are frozen after that, and they carry information about the energy of inflation in the terms of the amplitude of the tensor's power spectrum compared to a scalar power spectrum. And by knowing this, the energy of this, we will know a lot about inflation. And also we have that for the CMB, so the CMB is Thomson scattering projected into the sky, also has polarization, is polarized, and we can decompose the polarization into E modes and B modes, where the analogy with electromagnetism is direct. And the important part is that B modes depend only on the gravitational wave signal with initial conditions given by inflation, but what's produced later on matter and radiation domination. So now we know a lot about inflation, but we would like to improve our constraints. So this is the famous plot. And this will be my last thing to say about inflation. But we have constrained the tensor to scalar ratio, and that will put some constraint on what also are the constraints for modified gravity. So what will be important for us is that we have the following terms. So we have the initial conditions from inflation. Then we have the source function that in the case of B modes depends mostly on the gravitational wave signal at radiation domination and later matter domination. And all these effects are projected into the sky by this Bessel mode. So what one does is to take the signal, to decompose it into spherical harmonics. Then one figure out that it's only a two-dimensional projection, so we get rid of some terms, and we get that will be only dependent on the number of this mode. If we look at the signal, how does the signal for the source function how it looks like, we know that at large scales, it will depend on the kinetic energy of the gravitational wave evaluated at recombination times a draft factor. So this is for the B modes. So here the important is that there is no neutrino damping. So it will be a different signal. And this will be very important at large scale, but smaller scale we have different stuff, and other processes will take place. So we'll be mostly worried when we want to solve analytically our equations in this regime at large scale with mean at low L. So at matter domination, so we will have that these modes are out of the horizon for most of the time, so they carry a lot of information. And what will happen with gravitational waves is that they are out of the horizon. So a gravitational wave generically will be out of the horizon after inflation, then will start evolving, and at some time it will enter the horizon again, and this will happen at radiation or matter domination. And at matter domination, we'll have the large L modes where this signal that I talked before is more important, so it will be the most interesting place for us. So what we can do is, so if we have a set of equations, we have seen that modified gravity is very complicated, so we can try to simplify our things to see what will be the signatures by solving the equations on matter domination first, and then we will try to see what are the signatures there. So which signatures can we prove? So we have first that a modification of gravity, such as in Hordensky or beyond Hordensky theories, will lead to a different speed for the tensor modes. This is because there are higher curvature terms that will enter somehow, and then will lead to constraints which are it's not really, and they might be small, but there are no theoretical reason to know what they are small. So we can see what will happen with them. And the main effects will be that the main effects is that the time that the wavelength takes to enter the horizon will be modified. And because of the way of this, so because if you think of this as a signal that will enter the horizon when, so will peak when enter the horizon, because the horizon arrives at a different time, then that difference on time will be imprinted onto a CMB, so we can have plots like this where we can check what will be the difference with this. So we have that modifies the acoustic peaks. This is for the B modes. Also, yeah, so there's a chip. And then one can try to constrain what will be the difference of the speed by using these things, which one can find that's very small, but still some scenarios could be done. Also interesting, one tried to do something called disformer transformation, which is a change of coordinates, and to see what will means to have this kind of effects. Because by doing that, what we'll do will be to change the speed on the tensor mode for the speed on the scalar modes, and to see what will happen with the speed of the scalar mode, to see if there any effect that could be considered. And we found that it happens the same. So it achieved the acoustic peaks and also changed the damping scale. And that's very interesting because it's a similar effect to adding another species of neutrino, or having extra relativistic species. Now, when one tries to see massive gravity, we'll start with this equation, which is will break Lorentz invariance, but we will we don't care for now, so we'll take this model and to see what will happen. And we will consider first what will happen at matter domination. So one finds that one can approximate the solution at matter domination by the solution at massless, when the graviton is massless, which will be given by this part, but times the solution when the graviton is massive, which is given by this part from here. So one has only k squared minus a dot divided by a. One will find that the solution will be this part from here, which, as I told you before, it will enter the horizon and then it will leave. But if we take if we take only the m squared a squared, we'll find that it will be given by that part. Okay. And so one can try to see those kind of solutions. And we find that they have a very good approach, very good agreement with if we solve them numerically. So what will be the difference will be that the oscillations are different because we have those points from here, because it's a multiplication of the two oscillations, so it will be much faster, but we will are trying to capture in that solution is the time that it takes to enter the horizon, because this will be the part that will be important for the B modes. And we can see that we get a good approximation on over all scales. So then I showed you that psi will be proportional to the kinetic energy. So we take the kinetic energy and we find that obviously if this part is bigger than the other term, then the main contribution will be from H naught. So then the massive part of the solution won't be detectable. And in the other case, we have the contrary. So if Hm is bigger than the other part, which will mean basically that the mode is bigger than, that m squared a squared is bigger than k, we find that this part is bigger. And then in that case, we can see what will be the signatures of that. If we look at this, how the solution will be and what will be the difference, we will see that H naught is 0 because it's constant when it's out of the horizon. And then it starts oscillating when it enters the horizon, the kinetic energy. But for the case of the massive graviton, which is the one here, at recombination time, it will behave like this. So we have this constant term from here, which is also oscillating. And this will be a key signature of the B modes, what will happen with the B modes during massive gravity. So we put that into class. So if we simulate what will happen, we find that, okay, so this is the solution for a massless graviton, and this will be the solution for massive graviton. We will see that because of this different source term at matter domination, we have a kind of a plateau, and this is a very distinctive signal of this. So we increase the mass, and we find this. But also, if we look more carefully, we'll find that this mass is oscillating. One can then try to see what will happen with the BMOS, so we can do some estimation and find that the small l, this term for massless gravity grows as L squared, but we can find that it doesn't grow as L squared, but stays constant for small l. And if one try to calculate what will happen at large L and do some tricks and use the flat sky approximation, which is not really valid, so one should take this calculation too seriously, but just to say when it starts decaying, one will find that it decays at this time. So there will be two regimes. One will we find here that there is this plateau that starts decaying at L around 100. So obviously, this will be limited because we can only prove some masses. So for very low masses, that will be lower than k. So we have like a limited number of modes that we can prove, and there will be some masses which are too low to be proved, and so there is a limit that one can find. So in the case that, and that will depend on R. So for masses which are, if there is no detection of M, that will imply that the mass is lower than this. Okay, which is a better law than one will find by using other kinds of experiments. What to learn from here is that by detecting R, we will, if we get to detect R, we can constrain massive gravity at a greater precision. But also there are some problems with this theory of massive gravity. First, because it was Lorentz breaking, so it was breaking Lorentz invariant. So if we try to consider other theories which are Lorentz invariant, one has to deal with the RGT massive gravity. And usually, the way one tries, the main problem is that will be more gravitons, and these other couplings to matter to the other gravitons will introduce instabilities. So, and also, the way and the matter couples to the gravity will mean that it might be the case that there is no signal to be detected. So, some previous work have shown that in theories, the signal will be proportional to some coefficients, kappa 1, h1, kappa 2, h2, which will be model dependent. And we have to consider those two cases carefully. So for example, in this work from 2 years ago, they found for a theory of massive bigravity that doesn't have instabilities at these scales, there will be a massless graviton, which is Hij plus, and a massive graviton, Hij minus, but the coefficient will be very small, meaning that there will not be an effect of the massive graviton on the V spectrum. So, but we want to consider more, this is still not too general, so we want to consider the most general theory, so we're going to assume that both gravitons couple to matter, and we're going to see what are the effects that we get from there. So in this case, we are going to get this maze matrix, which is very general, and it's also symmetric, so Mi12 is equal to M21. And so we have that the plateau is a bit different, but still is still there. And then, okay, so to see what will happen, sorry. And then, so we can solve the equations, find an ansatz, and we'll find that in the case that's solvable, analytically, we will find that we have a graviton with masses between 0 and M11 plus M22 squared divided by 2. So we can consider the extreme case when there is a massless graviton and a massive graviton to see what will happen with the massive graviton. And if we solve everything, we will find that the coupling to matter will look like this. So what is important here is that this F naught ij is the massless graviton and Fmij is the massive graviton. And we find that the massless graviton depends on this coefficient. So in the case, for example, that M22 is similar to M21, then the effect of the massless graviton disappears. The massive graviton disappears. But we will never, it's very hard to get rid of the effect of the massive graviton. So this will be usually suppressed compared to this. Obviously, we can see what will happen and what are the cases we have. So we find that, for example, if we take different couplings to see how fast it goes away. So we had H naught here and a linear combination of the massive and the massless graviton, and I'm going to vary the coefficient of the massive graviton. We find that when one gets to, for example, 1/10, the effect is already suppressed, and if we go like 1/100 100, then there is no really difference between the massive and the massless graviton. Now, if we want to do these things serious, we have to consider that there is instability on the pressure sector that goes as this. So we have the real double couple theory has this term minus, which have a minus sign here. If one take the eigenvalues of the instability part, one will find that there are solutions that grow as, now there is a part that grows as 10 to the square root of 5 divided by 2. I want to see what will happen with these cases, if we want to use some of the analysis we did before for this minor instability. So first we solve the equations, and now we find that we can solve that because this is only a radiation domination. So after equality, we have the same solution than before, with some coefficient that will be given by can be solved analytically using Mathematica. But then we have this part from here. And the important part is that the solution will have this huge bump that goes to up to 200. That will mean that when we want to consider that because the power spectrum will be big at this part, it will be 200 to a square times bigger than the other one. So if we find again how the couplings are, we find that in this case, so we do exactly the same. We want to take a massless graviton and a massive graviton. We find that there it can be, and the instability will be in both on only of one of them. And we find that the instability, when we do the same than before, which is taking the determinant of the mass matrix equal to 0, is not on Fm, but it's on F naught. So you know that, as I told you before, this term can be 0, or can be small, has to be large, and this term can be small. But the problem here will be that this graviton solution will be much higher than this one. So we can't get rid of the instability by just tuning the masses. So if we look at the solutions, we'll find that this is for air equal to 10 to minus 2. You see that is the solution for the instability is 10 to the 5 times higher than the other one. But curiously, it's not too different if you look at it by this. So we normalize everything, and we look at the solutions from here, and we see that is different on the tail because there's a lack of power there. But on the large mode, it's mostly similar, and also that the behavior from massive graviton is still there. So we have that, I told you that there is this plateau that appears at large L, and because for the instability, large L is still dominated by matter, it's still the same solution because it's at matter domination, and then the difference is because since there is only one solution, it has to match, so it's still very large, but the plateau behavior will be similar to this. So what we learn from this is that if one takes some risks, can say that even if R is too low, we can have that because of the instability, the amplitude of the power spec of the BMOS will still be large. So there are things that it. Yeah. So now I'm reaching the conclusion. So, well, we can learn a lot of B modes by detecting this. And it will be interesting to see then how much can we constrain gravity now that we know how it will behave in this regime. If it's totally ruled out, or if we allow R to be very small, we can still get some results. Okay, that's it.
Sorry, question. So for the models you're considering, I mean, you know that there are really strong constraints on the type of models, branches, and all that because of instabilities, ghosts, and all. Mm-hmm. So you're taking those into account. So you're working with models that you're sure they're not excluded, right?
Yeah, I'm taking one branch.
Can you say which branch you're using?
I don't remember. Is this branch where B is equal to H?
So first of all, it's doubly coupled, right?
Yes, double coupled.
And probably non-dynamical branch, like the algebraic one.
No, it's the algebraic branch.
Okay, and you are getting self-acceleration and all that from that model?
Yeah.
Okay, thanks.
Yeah, it's a model we know that it will work, but has this instability.
Okay, then thanks again, Sebastian.
you.